So we can put together what we know from this unit and what we've learned before in algebra to sketch a graph of some complex functions here. So this first example, we have f of x, which is a quartic function or a fourth degree polynomial function. And if I remember, I might remember that the end behavior of a fourth degree polynomial or an even polynomial with the positive coefficient is that as x approaches infinity, my graph of f of x is also going to approach infinity. And on the left-hand side, I don't know why I did the right-hand side first, we will also approach infinity. So I know my end behavior. I could also easily find my y-intercept. So my y-intercept is when x is 0, and that's going to be 2. So right now, I know the ordered pair 0, 2 is a point on my graph of f. So we could also use information about where our function is increasing or decreasing. So when I find my first derivative, let's see, we've got 4x cubed minus 4x. And when I set my first derivative equal to 0, I'm going to first put this in factored form. So I could factor out a 4x. And I'm left with x squared minus 1, which is, of course, a difference of squares. So I could factor this down to x minus 1 times x plus 1. So when I set my first derivative equal to 0, using the zero product property, I'm going to get the solutions that if 4x equals 0, x equals 0. If x minus 1 is equal to 0, x equals 1. And if x plus 1 is equal to 0, x equals negative 1. So I'm going to make a number line, like I have been, because we're looking for really like relative mins and maxes, or we could think of just looking for intervals of increase and decrease. Both of those will help us graph here. And so on my number line, when I test this, I'm always going to use the factored form of my first derivative, because multiplication rules are much easier to use when we're just determining the sign of a number. So if I plug in, say, like a -2 here, 4 times a -2 would be a negative number. -2 minus 1 would be a negative number. And -2 plus 1 would also be a negative number. So a negative times a negative times a negative means f prime is negative there. So f is decreasing on that interval. If I plug in a number between 0 and -1, let's say like -1/2, well, 4 times that number will be negative. X minus 1 will be negative, but x plus 1 now will be positive. So a negative times a negative times a positive gives us a positive product. So f is increasing on that interval. Let's say we plug in a positive 1/2 between 0 and 1. Well, 4 times a half is positive. 1/2 minus 1 is negative. 1/2 plus 1 is positive. So we have a positive times a negative times a positive. F prime is negative, so f is decreasing. And finally, on the other side of the 1, I could plug in a 2. You could plug in any number you want that's greater than 1. 4x is going to be positive. That number minus 1 is going to be positive. That number plus 1 is positive. So f is increasing there. So we have also determined that we have a relative minimum at -1 and a relative maximum at +1. Oh, nope. Sorry, at 0. And then another relative minimum at 1. Okay, so we have a min, a max, and a min. Wow, I said the right word and I wrote max. I was still stuck on the 0. All right, so if we wanted to go ahead and find those, we would just find the output. I need to just plug those values back into my function f itself. So if I think about what is f of -1, I should get a +1. So I get this ordered pair -1, comma, +1. F of 0, well, we already know that that's going to be 0, comma, 2. That's our y-intercept. And when I plug in a +1, 1 to the 4th minus 2 times 1 squared plus 2, that's going to give me a 1 again. So I get 1, comma, 1. All right, so if I go ahead and plot these points on my graph, I've got -1, comma, 1. We already have 0, comma, 2 on our graph, and then we have +1, comma, 1. So right now, this is something I know about my graph. I also know my end behavior is up, up, but we'll come back to that. So the last thing we could check to make this really as specific as we can, graphing this way, is we could look for the points of inflection or changes in concavity. So if we find our second derivative, that's just going to be 12x squared minus 4. And all I could really do here is factor out a GCF of 4. So that becomes 4 times 3x squared minus 1. That's our second derivative. When we set that equal to 0, well, I know 4 isn't equal to 0, so I'm really concerned with where 3x minus 1 is equal to 0. That's when 3x squared is equal to 1. So x squared is equal to 1/3. So x could be positive or negative the square root of 1/3, which is 1 over the square root of 3, which is root 3 over 3. So on my number line, when I'm testing for concavity, I have to consider the negative square root of 3 over 3 and the positive square root of 3 over 3. And I want to consider the sign of my second derivative. So when I go ahead to plug a value in there, I know that the square, like if I think about the square root of 3, I know that's a number that is less than 2, greater than 1, right? And I'm dividing that by 3. If this kind of helps me approximate it, it's about 5.7. It's close to 0.6. Or sorry, not 5.7, 0.57, 0.57. So you could check that in the calculator if you want to double check me. When we go ahead to test our number line here, I just need to make sure that I'm on the left-hand side of negative 0.57. So we could just start with plugging in a -1 to our second derivative. That would be on this interval. So when I plug that in, again, just like before, I'm always going to use my factored form, even though in this case I couldn't really factor this any further. So like a -1 squared times 3 minus 1 is a positive number, and we're multiplying that with 4, which is also a positive number. So our second derivative is positive here, meaning that our function is concave up. For that next interval, I'm probably just going to choose 0. That's my favorite number between negative root 3 over 3 and positive root 3 over 3. When I plug that into my second derivative, 3 times 0 minus 1 is -1 times 4 makes my second derivative negative there. So f is concave down. And then I could plug in a positive 1 on the other side. I would again get 3 minus 1 times 4, which is a positive number. So f is concave up. So if we want to just approximate where those are on our number line, I would probably really need a calculator to effectively plug that back in. So I'm just going to approximate it. That negative root 3 over 3, we said that's about negative 0.57. So I don't know, like here-ish, that's about where we're going to change concavity. And then also at about positive 0.57. So what we know is that our function is concave up from -∞ to about negative 0.57. So when I go to sketch this graph, I know that my function is curving up until we get to about here. And then it curves down until we get to about here. And then it changes concavity again and curves up. So that is by no means a perfect graph. In fact, it looks a little bit wonky. But that is roughly what our graph would look like there. So again, we can use those two things that we have learned in combination about how the sign of our first derivative informs what we know about our function, and how the sign of the second derivative informs what we know about, well, the concavity of our function, to make a fairly accurate graph there. All right, so for this next example, this one, if I were to first look at this function g, I wouldn't really know how to start that graph. So again, if we think about the end behavior, I like to start there. Well, the limit of g as x approaches positive infinity, well, x squared times e to the x, that blows up, and that becomes, well, infinity. But when we find the limit of g as x approaches negative infinity, we get infinity times 0. And so we know that when we get infinity times 0, that's an indeterminate form. And we typically want to rewrite that so that I can get something in my denominator. So I'm going to rewrite g of x to be x squared divided by e to the negative x. And so now the limit as x approaches negative infinity, when we plug this in, we get infinity over infinity. So we have two choices here. We could use L'Hopital's rule. We could use L'Hopital's rule to evaluate this limit, or I could just think about the growth rates, that as I'm plugging in increasingly negative numbers, my denominator is blowing up because it's making my denominator huge positive numbers, and it's blowing up faster than my numerator. So the value of this limit is 0. But alternately, again, if we use L'Hopital's rule, we could just keep taking the derivative using L'Hopital's rule until we get to a limit that will give us the value of 0. Okay, so if we go back now and think about our, actually, let's find our y-intercept real fast. I was going to go to the derivative, but the y-intercept is something else that's easy to do. My y-intercept always occurs when x equals 0, so 0 squared times 1 is 0. So we know that is a point on our graph, and I'm going to go ahead and I'm going to put 0, 0 on the graph. I'm going to remind myself over here that my function's blowing up. And I'm going to remind myself over here that I'm approaching 0 on the left. All right, so now let's take a look at our first derivative. So g prime of x is going to be 2x e to the x plus x squared e to the x. And again, I'm going to want to factor this. So I'm going to pull out a GCF of x e to the x, and I'm left with 2 plus x in parentheses. So again, I'm looking for critical values. This is never undefined. So if I set g prime equal to 0, using the 0 product property, x could equal 0, e to the x could equal 0, except it can't because e to the x is not 0, and 2 plus x could equal 0. So we get two critical values of x equals 0 and x equals -2. So if I go ahead and put those on a number line, if I'm looking at the sign of my first derivative, again, I always want to use this version of it in factored form here. Let's say I pick a -3 to plug in. Well, my first factor x is going to be negative. My second factor e to the x is always positive. And if I'm plugging in a -3, 2 plus x is going to also be negative. So a negative times a positive times a negative is a negative product. Is a positive product. A negative times a negative is a positive. That was my mistake. So g is increasing on this interval. If I plug in, let's say a -1 between -2 and 0, again, x is negative, e to the x is positive, but 2 plus -1 is also positive. So I get a negative times a positive times a positive. That is a negative product for g prime, so g is decreasing. And then when I plug in a positive number on the right side of 0, let's say 1, I get a positive times a positive times a positive. So g is increasing. All right, so if I wanted to find, again, we have a relative max at x equals 2, a relative min at x equals 0. I was just looking at the wrong arrows when I said that. If I want to find the actual value of that, again, I would have to plug that back into g. So like g of -2 is going to be 4e to the -2, which is 4 over e squared. And I know that e squared is a number that's like between 4 and 9. So that could help me approximate that value. And then we already know that when we plug in a 0, that g of 0 is 0. So that's the location of my relative min. All right, so when we think about graphing -2, 4 divided by e squared, that number is going to be a little bit less than 1 because, again, we said we know e squared is going to be a number between 4 and 9, and it's actually going to be closer to 9 than it is to 4, so just something to think about when we're evaluating that. I'm just going to estimate where it is on the graph, so let's say maybe about here would be our -2, 4 over e squared point. All right, so we know that's the location of our relative max. So then finally, if we wanted to think about the concavity of our function, we would need our second derivative there. So when I find my second derivative, let's see, this time, I mean, don't think I want to use the factored form. I think I want to use the terms up here. I mean, either way, we have to do the product rule more than once. I think it'll be easier using this one up top. So 2x e to the x becomes 2 e to the x plus 2x e to the x. And then the derivative of x squared e to the x, well, that's this whole thing. This is the derivative of x squared e to the x. So I get 2x e to the x plus x squared e to the x. And I could go ahead and combine these terms in the middle. So 2 e to the x plus 4x e to the x plus x squared e to the x. And when I go ahead and pull out my greatest common factor, it looks like my greatest common factor there is going to be e to the x. So I get e to the power of x, which is 2 plus 4x plus x squared. And I'm going to rewrite that in standard form. I don't know, that'll just drive me crazy. All right, so that's our second derivative. And we know it's never undefined. So I want to consider where it's equal to 0. I'm just running out of space here. All right, we know e to the x is never equal to 0. So I'm really just looking for where x squared plus 4x plus 2 equals 0. And unfortunately, that's not factorable. So I could use the quadratic formula. X equals opposite b plus or minus the square root of b squared minus 4ac, all of that over 2 times a. So we get -4 plus or minus, let's see, 16 minus 8 is the square root of 8, all of that over 2. And I could change that root 8 to be a 2 root 2 because that will help me simplify this a little bit. We end up getting -2 plus or minus the square root of 2. So our x values are -2 minus root 2 and -2 plus root 2. All right, so if we put those on a number line, if I think about my second derivative here, when I'm picking a value to the left of -2 minus root 2, I could really pick any number that I want. And remember, like the square root of 2 is roughly 1.4, if it helps us to kind of remember that. It's 1.4 and some change. So -2 minus, let's just say 2, would give us like a -4. So I need to maybe go out to at least like -4 or -5. When I plug that into my second derivative, again, I'm going to use the factored form that we got right here. I know e is always positive. When I plug in, let's say, a -5 here, I'm going to get 25 minus 20 plus 2. My brain is too tired to do that math in my head. So my second derivative is going to be positive on this interval, meaning that g is concave up. Then let's say I pick a point between -2 minus root 2 and -2 plus the square root of 2. So how about -2? That number would be between those. Again, I know e to the power of anything is going to be positive, so I'm just going to think about what happens when I plug -2 into this part. So I'd get -2 squared plus 4 times -2 plus 2. That is a negative number there. So g is concave down on that interval. And then to the right of negative 2 plus the square root of 2, how about we just plug in 0? E to the 0 times 2 is positive. So we are concave up again. All right, so I'm just going to approximate on the graph where negative 2 minus the square root of 2 would be. So that's going to be roughly at like negative 3.4, because it's roughly negative 2 minus 1.4 approximately. And then that means this is going to be roughly at positive 0.6. So on my graph, I'm like, all right, we've got at negative 3.4, that's going to be like here-ish. I just know that this point is going to be between that maximum and getting closer to the 0. So I don't know, I'm just going to put a point here. That looks like it's roughly at about negative 3.4. And at negative 0.6, that would be maybe about here. So if I think now about the concavity, we said this is going to be concave up until it gets to this point. Then it's going to be concave down. So kind of looks like that. And then at this point, it's going to change concavity again and be concave up. All right, so we know we're going to have that type of end behavior. Going this way, we're going to approach 0. So that's fairly tedious, but kind of fun, because we can really use that as a powerful tool to be able to imagine functions, what they look like graphically, when otherwise that would be really hard to graph. Well, without a graphing calculator.